Hi there, Mr. Sutton bringing you the AB Calculus Chapter 5 Quiz 3 Practice Solutions for Fundamental Theorem of Calculus. On this problem, we have this big F function defined as the integral from 0 to x of e to the negative t squared. We want the derivative of that. Since we're taking the derivative of an integral that has an x in the upper limit, we'll just substitute x for the dummy variable t. So this will be just e to the negative x squared then. And is that an answer choice? It sure is. Choice E, ironically. On this problem, we're given this integral function from 0 to x of 1 over the square root of t cubed plus 2. Based on that, we want to know which of the following is false. So first one, f of 0 equals 0. Well, if you plug 0 in for the upper limit, you have an empty integral, so that always has a value of 0. So choice A is actually true. So we wanted the false one. Choice A is not what we're looking for here. Choice B, f is continuous at x for all x greater than or equal to 0. Well, the only way to get discontinuities out of any of this is if the whole denominator equals 0 or if the whole denominator is somehow negative. Well, you can't get a negative if you're plugging in an x value here that's greater than or equal to 0. So really the only thing you could possibly do is try to make this whole thing come out to 0. But to do that, let's see, if you set this stuff equal to 0, that's going to be negative 2 cube rooted. Well, we can't plug in negative cube root of 2 because, again, x has to be positive. So this is a true statement. As long as x is positive or 0, we're steering clear of these values here. They're going to make this radical either 0 or negative. Next, f of 1 is greater than 0. So is the integral from 0 to 1 bigger than 0? Is it positive? All this stuff is going to be positive area. Square root can only return positive numbers if it returns anything at all. It could return 0, but again, we don't have the t value that we would need to actually get 0 out of this. So because this is only going to be positive, we're only going to be getting positive area. So going from 0 to 1 is going to give us positive area. So positive integrand means positive area, at least if you're going in the positive direction to the right. Next, f of 1 is 1 over, or f prime of 1 is 1 over the square root of 3. Well, if I take the derivative of this function, I'm just substituting x for t. So that's just 1 over the square root of x cubed plus 2. And then if I plug 1 into that mess, I've got 1 over the square root of 1 cubed plus 2, which is just really 1 over radical 3. So that ends up being true. So by process of elimination then, we're stuck with choice E, but let's just analyze it just to be sure. So here they're saying f of negative 1 is greater than 0. So if I go to negative 1, well, what's happening there? I've still got positive area, because this stuff doesn't become negative until I plug in negative cube root of 2, which is actually to the left of negative 1. But because I'm going to the left on area that would normally be positive, it ends up actually having a negative value for the integral. So we're above the x-axis, but still integrating backwards. So then choice E is false, and that's the answer that we want. On this problem, we're given this integral function from 1 to x squared of square root of 1 plus t cubed. We want the derivative. Since I'm taking the derivative of an integral with x squared as the upper limit, I'm just going to substitute this upper limit for the dummy variable and then multiply by the derivative of x squared. So we're going to end up with the square root of 1 plus x squared cubed times the derivative of x squared, which is 2x. Cleaning this up a little bit, I can move that 2x out in front, and this is really just 1 plus x to the 6th power. So that ends up giving me answer choice A. On this problem, f is defined as this integral function here, with some pretty crazy limits of integration if we're being honest. The integrand doesn't look that much better, so we want to know, based off of this, at what value of x is f of x a minimum. So to figure this out, we're going to get f prime of x and see what the critical values are for that. So f prime of x, I'm just essentially plugging this upper limit into the dummy variable and then multiplying by the derivative of this to satisfy the chain rule. So I can rewrite this f prime as e to the x squared minus 3x squared times the derivative of x squared minus 3x, which is 2x minus 3. All right, so there's my f prime. Now I want to figure out critical values for this thing. So there's no way to make e to all this stuff equal 0, so I can just disregard that. But over here, 2x minus 3, that's going to equal 0 at 3 over 2. So that's actually my only critical value that I end up getting out of this. Now, in order to figure out if this is a min or not, there's two ways you could do this. One would be to put this on a number line and do some sign analysis around it using the first derivative. Another way would be to get the second derivative and just see if that comes out positive or negative. Now, the second derivative, if you look at this, is going to require the product rule and a whole lot of stuff inside there, so that's probably going to be annoying to do. I'm just going to go straight to the number line and test around f prime. So we've got 3 over 2, and to the left of 3 over 2, let's see, what could I plug in here? Let me plug in just 0. That's an easy number, right? Now, as you're doing your sign analysis here, this e term always has to come out positive. There's no way to get a negative out of this because we're starting with a positive base. So we can just disregard what e is doing. It's really just down to this 2x minus 3 part. If I plug in 0, I end up with negative 3, which is negative. And now something bigger than 3 halves, like 2. If I plug 2 in here, well, that's 4 minus 3. That comes out positive. So pretty easy sign analysis if you disregard this e term. So since f prime is changing from negative to positive at 3 halves, that tells us we have a relative minimum at x equals 3 halves. Now they wanted the value, the minimum value for the entire function. So 3 halves is one of the answers. However, one of the answers is also no value of x, which is to say there is no minimum. Here's what we're actually trying to do. We're trying to establish that we have an absolute minimum of 3 halves on a function that is not a closed interval. The extreme value theorem says if you have a closed interval in a continuous function, you're guaranteed to get extremes, absolute extremes, but it says nothing about open intervals. So how do we reconcile this? Well, 3 halves is the only critical value across the whole function. So since it's a relative min, that means if you just look at the sign analysis here, we're decreasing all the while until we get there. So that means that all the stuff that came before 3 halves must have been bigger. And we're increasing all the while after we get there. So all the stuff that comes after x equals 3 halves is going to be larger as well. So that means, since it's the only critical value, x equals 3 halves must also be the absolute min for the graph. So that allows us to safely choose choice C. On this problem, we're given the graph of f prime, derivative of f. If f of 0 equals 0, which of the following must be true? So let's just go through these and see what we can eliminate. So option 1, statement 1, f of 0 is larger than f of 1. Well, f of 0 is 0. F of 1 is going to be essentially 0 plus all this positive area here. For that reason, f of 0 definitely can't be bigger than f of 1, because by the time you go from 0 to 1, you've already gained all this positive area. So if anything, f of 0 should be less than f of 1. So we can eliminate choice 1. F of 0 is positive, or f prime is positive from 0 to 1. Therefore, f is increasing. So there's no way that f of 0 is greater than f of 1. All right, next statement, f of 2 greater than f of 1. Well, between 1 and 2, we've gained even more positive area. So this would be a true statement. F prime is greater than 0 on 1 to 2. So again, f is increasing, allowing us to have something bigger at f of 2. Last statement, f of 1 is larger than f of 3. So as we go from f of 1 to f of 3, we've got all this positive area that we've racked up, And we also have a little bit of negative area down here, but definitely not nearly as much as we had positive area. They're basically saying here, if f of 1 is greater than f of 3, they're essentially saying that from here to here we end up at a lower value. But that just can't be. The negative area between 2 and 3, which would drag us down and give us even a chance of having f of 1 being larger than everything after it, this negative area is too small to offset all this positive area. So that means overall that f of 1 has to be less than whatever f of 3 is. So this is a false statement as well. So only statement 2 ended up being true, so that would give us choice B. For this problem, for all values of x, the continuous function f is positive and decreasing, which is kind of interesting because it stays above the x-axis, but it's decreasing all the time. G is a function given by the integral from 2 to x of f, which of the following could be a table of values for g. So it helps if you have a visual for this one. A good one to use is e to the negative x, which looks like this. It's essentially a decaying exponential function. It's continuous, it's above the x-axis, so positive, and it's always decreasing. So in light of this, let's see if we can start to analyze some of the values in these tables now. Let's start with the 1s here. So if you're doing the integral from 2 to 1 of f of t dt, you're essentially going backwards. And you're going backwards on what's positive area. This is all going to be positive area normally. But if we're going backwards on positive area, that means it ends up being negative area. So since going backwards on positive area gives us negatives, we know that the integral from 2 to 1, or simply put f of 1, or actually this would be g of 1, has to be less than 0. So looking at our values in tables, for a and b, the g of 1 there is less than 0, so that checks out. But for c, d, and e, g of 1 is not less than 0. It's not negative. So c, d, and e actually can be tossed out for that reason. All right, so we have to figure out a way of separating a and b. The only main difference between these is that a appears to be slowing down in terms of how much it's growing, whereas b appears to be speeding up. So if you take a look at this, as we move further along, we've got an area that it's getting smaller and smaller. So we're adding less and less as we go. So since the amount of area gained at each step is decreasing with this positive decreasing function, that means that we would expect the difference to be going down. So that would actually be choice A. Choice B, we're increasing the amount of area gained, not decreasing it. So because it's not B, that leaves us with choice A. For this problem, if n's a non-negative integer, then integral from 0 to 1 of x to the n equals integral from 0 to 1 of 1 minus x to the n for what? So what are the different values of n that make this true? Well, to figure this out, I'm actually going to go ahead and evaluate both of these integrals and see what it comes out to, and then we'll compare those expressions at the end. So for this first one, I need to use my reverse power rule. N is a constant because x is the variable here. So this gets bumped up to the n plus 1 power, and we're dividing by n plus 1. So we're basically plugging in 1 and 0 for x in this situation. So that's going to be 1 to the n plus 1 over n plus 1 minus 0 to the n plus 1 over n plus 1. Well, 0 to anything is going to be 0. So this is just 1 to the n plus 1, or this is actually just 1 really, right? 1 to any power is also just 1. So we just have 1 over n plus 1 when the dust settles. All right, a lot of fancy simplifying happened there. Let's go ahead and do the other way now. So for this, we have to be careful on this one. This bumps up to an n plus 1 again, and we're dividing by n plus 1, but we also have to divide by the interlinear tail of negative 1. So this then comes out to negative 1 minus x to the n plus 1 over n plus 1. Plugging in 1 and 0 for that, we've got 1 plugged in for x there. We've got 0 plugged in for x. And what does all this craziness come out to? Well, up here, this is really just 1 minus 1 inside, which is 0. and if you negate it or raise it to power 0 is still 0. So this n plus 1, this whole first fraction is actually just going away. So that means it's up to the second fraction. Let's see what this evaluates to. So this is 1 minus 0, which is just 1. Raising that to the n plus 1 is still going to be 1, but now we have this negative up here. So we end up with negative 1 over n plus 1. But now this negative and this negative can cancel. So this is really just 1 over n plus 1. Since this is equivalent to what we had before, that means that this equation holds true for all n values, not just certain ones. So choice E. On this problem, we're given the equation integral from 1 to k of x to the n minus 1 dx equals 1 over n, and we're trying to solve for the k value that makes this true. So I'm just going to go ahead and evaluate the integral on the left, and then I'll figure out what to do with that k once I see it actually as part of some real equation. So taking a look at what we have here for antiderivatives, this n minus 1 is a constant. If I bump that up by 1, that just becomes n, and I'm dividing by n. So I have x to the n over n from 1 to k still equals 1 over n. Let's expand this part now, though. This is going to be x to the k, or actually, no. This is just going to be k to the n over n minus 1 to the n over n. And again, we're saying that equals 1 over n. We can actually merge these together since we have a common denominator. And we can actually just multiply everything by n and eliminate those. So we have k to the n minus 1 just equals 1. Adding 1 to both sides, we end up with k to the n equals 2. And to solve this equation, n, again, is just a constant. So if I want to get rid of a constant exponent, I just have to raise both sides to the reciprocal of that exponent, the 1 over n in this case. So then I can say k equals 2 to the 1 over n, and that's going to be answer choice D. For this problem, we have the integral of some unknown function from 1 to 4 is 6. Based off of that, we want the value of some other integral from 1 to 4 of that weird function with a 5 minus x in it. Okay, so how do we get started on this? I find that when in doubt, I'm just going to actually evaluate these integrals and see what I end up with. So for this first one, the antiderivative of f is big F. So I've essentially got big F of 4 minus big F of 1. And we know that that equals 6 because they told us that integral is 6, and this is essentially doing what the integral does. That's not enough to do anything with at this point, but it might be useful later, so let's keep going. We're going to do the same and evaluate this next one. So the antiderivative for this one is going to be big F of 5 minus x divided by negative 1. So negative big F of 5 minus x. And then we're evaluating that from 1 to 4. So I have negative 5 minus 4 minus negative big F of 5 minus 1. So we're going to be adding that last one there because we're subtracting a negative. Cleaning this up a little bit, this is really negative F of 1 and positive F of 4. So I could just rewrite this as big F of 4 minus F of 1. And hold on a sec, didn't we just say up here that that was equal to 6? Well, that hasn't changed. So that means that answer choice A is our friend on this one. This problem is actually a pretty quick one. Let's say that p is a polynomial of degree n, greater than 0. We want to know the degree of the polynomial q of x equals integral from 0 to x of p of t dt. So in this problem, we're going to have to take the antiderivative of this polynomial that had degree of n. Since it's a polynomial, that means the reverse power rule works on it, which means you would have to add 1 to the exponent and then divide by the new exponent. So that means you'd be adding 1 to this n. Since the antiderivative of a power function is always 1 degree higher, that means choice E, n plus 1, is the way to go on this one. For this problem, we just want the integral from 1 to 2 of x to the negative 3. So for that, I'm going to use my reverse power rule. This negative 3 gets bumped up to a negative 2. Dividing by that, we have negative 1/2 times x to the negative 1/2. So essentially negative 1 over 2 times x squared. Plugging in these numbers now, that's going to be negative 1 over 2 times 2 squared. And then plugging in 1, we've got, we have to subtract this now, so minus, and then inside my little bracket, negative 1 over 2 times 1 squared. So over here, this is negative 1/8. And we're going to need to simplify because all the answer choices are simplified. Over here, this is going to be plus 1/2. So I've essentially got negative 1/8 plus 4/8. That's a grand total of 3/8. Answer choice D. On this problem, I want the integral from 0 to pi over 3 of sine of 3x. Let's start with our antiderivative. That's going to be, let's see, negative cosine of 3x. And then we have to divide by the tail of 3, so negative 1/3 cosine of 3x. So splitting that up, I've got negative 1/3 cosine of 3 times pi over 3 minus negative 1/3 cosine of 3 times 0. So I can just add that then because I'm subtracting a negative. Going through now, this 3 and this 3 cancel. So this is really cosine of pi, which is negative 1, times the negative 1/3 gives us positive 1/3. And then over here, we're also going to get positive 1/3 because this is just cosine of 0, which is just 1. So adding those two 1/3s together, we end up with 2/3, which is choice D. For this problem, a little bit tricky, we're asking which of the following is equal to ln of 4. So going through these answer choices here, well, you can't just add the stuff inside the ln's by adding the ln's themselves. This would actually be ln of 3 times 1, which is not the same thing. Here, there is no way to really divide ln's and then divide the numbers inside of them, so this doesn't work either. For this one, choice C, well, that has some potential at least, except that the antiderivative of e to the t is just e to the t. This would just be e to the 4 minus e to the 1, which is not equal to ln of 4. On to the next one. Well, I don't even know the antiderivative of ln of x, so that's probably not going to give us ln of 4 in any case. And then over here, well, the antiderivative for 1 over t is actually ln of x. So this one I can call ln of 4 minus ln of 1. So if I take my my anti-differentiated function here, plug in 4 and 1, I end up with this, but you might be saying, well, hold on a sec. Where did the ln of 1 go? Well, ln of 1 is just 0. So this is really just ln of 4 when you get down to it, which gives us answer choice E. For this problem, we're trying to find the integral from negative 1 to 3 of this piecewise function here, or at least figure out what numbers our integral is between. Since this is a piecewise function, we have to be mindful of border values. Negative 1 is contained in this first rule here between negative 2 and 2. But to get all the way to 3, we're going to have to cross out of this first rule into this second rule here. So I'm going to need two integrals to figure this out. I need the integral from negative 1 to 2 of 8 minus x squared. And I need the integral of 2 to 3 of just x squared. All right, let's go ahead and use our fundamental theorem to evaluate this. So this will be 8x minus, bumping that up to a 3, we've got 1/3 x to the third, evaluated from negative 1 to 2. Over here, this bumps up to a 3, so that's 1, and dividing by 3, that's 1/3 x to the third, evaluated from 2 to 3. So now we're going to plug 2 into all this stuff, and we're going to subtract all this stuff with negative 1 plugged in. And over here, I've got 1/3 times 3 squared minus 1/3 times 2 to the third. And I should have said 3 cubed there. There we go. Going through and cleaning this mess up a bit. So we've got 16 minus, let's see, this will be 8/3. This would have been negative 8, but we're subtracting, so that's positive 8. This would have been positive 1/3, but we're subtracting, so that's minus 1/3. Over here, this is 1/3 of 27, so 9. And here, this is a minus a third of 8. Okay, time to clean this up a little bit more. 16 and 8 is 24, plus 9 is 33. And then for the rest of it, we've got all the same denominators, so that's helpful. And for my numerators, I've got negative 8, minus 1 is negative 9, minus 8 is negative 17 over 3. 33, we could call that actually 99 over 3. 99 minus 17 gives us 82, so that's 82 over 3 that this comes out to. And we need this because we need to know what numbers this actually falls between for this. So 82, that's a little bit bigger than 81. 81 divided by 3 is 27. So this is definitely going to be in that range from 24 to 32. For this problem, we're trying to find the integral from 0 to pi over 4 of tan squared of x. So this one's a little tricky because we don't really know the antiderivative of tan squared. So what we're going to do is convert it into something we do know the antiderivatives of. Tan squared is part of one of those Pythagorean identities. The whole identity goes 1 plus tan squared equals secant squared. So if tan squared is all by itself, I could rewrite that as tan squared equals secant squared minus 1. So here's what we're actually looking at for a function here. And this is good because we know the antiderivative of secant squared is just tan. So that's tan of x. And antiderivative of negative 1 is just negative x. And again, evaluating that from 0 to pi over 4. Okay, well, we're going to have all this stuff with pi over 4 plugged in, minus all this stuff with 0 plugged in. Over here, I happen to know tan of pi over 4 is just 1. So we've got 1 minus pi over 4. And this stuff over here, well, tan of 0 is 0. 0 is playing itself here. So all this stuff over here just comes out to 0, leaving us with 1 minus pi over 4 as our final answer, so choice B. On this problem, I want the integral from negative 1 to 1 of this piecewise function. Since my border value of 0 falls on the interval of integration here, I'm going to need to split this up into two integrals. I have an integral from negative 1 to 0 of x plus 1, plus an integral from 0 to 1 of cosine of pi x. So time for these antiderivatives. This is going to be 1/2 x squared plus 1 going inside that first brackets. And then over here, this is going to be 1 over pi times sine of pi x, again from 0 to 1. Let's evaluate this now, because none of the answer choices look like this. So we've got all this stuff with 0 plugged in, minus all this stuff with negative 1 plugged in. Over here, I've got 1 over pi sine of pi times 1, minus 1 over pi sine of pi times 0. All right, let's go and see if we can clean all this up. So this first bracket just comes out to 0. For this next one, this ends up being, let's see, this is just a positive 1. So we've got 1/2 minus 1. That's a negative half inside, but we're subtracting it, so it's actually a positive 1/2. And then over here, sine of pi is what this is. That ends up being 0. Sine of 0 also ends up being 0. So when the dust settles, only 1/2 is left, which is choice D.